Hello, so this is question 13, and we have to draw a circuit diagram of the first order low pass filter with a resistor R1, a feedback resistor R2, and a capacitor C. So let's start with part A. So for part A, we have a low pass filter, so we have a resistor R1. This goes to our op amp, this goes to the ground, this is R1. Here we have the capacitor, so here is V out, this is VI, here we have a resistor, so C, and this is R2. And derive expressions for its transfer function, DC gain, and 3 dB frequency. So this is the circuit that we have. Let's start with the transfer function. So part B, let's call part B transfer function. So remember that if you assume like a DO op amp, remember that we have V plus equals to V minus, and also the currents as 0, right? So those are the assumptions for the ideal op amp. And then because we are performing an analysis in a circuit with a capacitor, it's usually like easier if we convert that capacitance to a reactance, and then we can analyze it in a frequency domain. So it's 1 over j omega c, right? Now, if we look at the circuit, we notice that the non-inverting input here is grounded, right? So the first conclusion on our first analysis is that V plus is equals to 0 volts. And this also implies that V minus is equals to 0 volts because of the first assumption of the ideal op amp, right? So now that we know the voltage at this node here, right, we can apply KCL at that node, and then we can equate the currents equal to zero, and then that from that point onwards we can basically derive our voltage transfer function. So in this analysis we have a current flowing in this direction here, we have another current here, and we have another current here, right? So the first current, we can derive it as V minus VI divided by R1 plus the second current, or the sum of the two currents, right? That is just V minus, because remember this reactance XC here, it's in parallel with R2. So if we take V minus, which is the potential here, minus V naught or V out, that's the potential there, and divide by the parallel between the resistor and the capacitor, which means R2 times 1 over j omega c, and then this entire thing here divided by R2 plus 1 over j omega c. That's the second current, or the sum of these two currents here, right? And that should be equals to 0. Okay, so again, if we, this equation is pretty similar to the second part of the problem 12, but if we keep simplifying this equation here, we can again multiply. So we multiply here by j omega c, and down here by j omega c, which is the same as multiplying by 1, right? So that equation becomes V minus V input divided by R1 plus V minus. So let's simplify one thing. So because we know that V minus is equals to 0 volts, right? So let's get rid of this V minus here and this V minus here. So let's keep with just the input here divided by R1 plus or minus, right? Minus V out. And now if you look at this part of the equation, so this one here, this numerator of our denominator here, this is the entire denominator, this becomes just R2, right? So we have just R2 down here, right? And if we look at this part here, which is the denominator of our denominator, it goes it multiplies the numerator here, V minus minus V out. And if we analyze this multiplication here, it's the same as 1 plus J omega C R2. So that's the equation that we have. Now from this point we can isolate, so in that should be equals to 0. So now if we isolate V out over Vi, right, we can just pass this one here to the right hand side, and then we divide both sides by Vi. This is the same as minus R2, and I'll separate divided by R1 times 1 over that 1 plus J omega C R2. Okay, so I'm splitting in two in these two multiplications. You see in a bit why. It simplifies the analysis of the DC and the 3 dB frequency. Okay, so this is the voltage transfer function. Okay, so if you want, you can write this entire equation here equals to H of J omega. Okay, that's the voltage transfer function for this circuit. Now the third part, part C, we have to define the DC gain. So let's see what happens with this equation at DC. Okay, so part C, DC gain. Now remember that DC means zero frequency, right? So omega equals to 0. Now if you look at the magnitude, the DC gain, so we are interested in the magnitude of H of J omega. This is the same as R2 divided by R1, right, because you get rid of that minus sign, times 1 divided by the magnitude of this complex number. So it's 1 squared plus omega C R2 squared. Okay, just the squared, it's inside the square root. Right? This is the equation for the magnitude, right? Now, if we substitute omega equals to 0 in this equation here, which is our DC gain, so omega of 0, this is just equals to, so if you look at here, omega equals to 0, it will zero out this number here. And then we are left with 1 divided by square root of 1 squared, which is just 1. So we are left with R2 divided by R1. Right? So that's the equation for the DC gain, okay? So this is the equation for the DC gain, okay? Now the fourth part is the 3 dB frequency. So let's see one thing here. So first we know that we have a constant gain, right? So if we look at the voltage transfer function, this here, it denotes a constant gain, right? So this constant gain, it basically means that if the frequency is too low, that this term here, J omega C R2 here, it's much less than this one. Basically, this is the gain that we have. So this is a fixed gain at low frequencies. Now, if you see you see on the body plot on the final part of this problem, but if you keep increasing the frequency, eventually this term here, it becomes more relevant than this one here, right? And then we start to decrease the voltage transfer function. Remember, this term R2 over R1 stay constant throughout the frequency range, right? But this term here, depending on the value of the frequency, it increases and then it becomes more relevant than this one. And eventually this ratio here between 1 divided by j something very high, it starts to decrease the magnitude of our gain, right? So the 3 dB frequency point is exactly the point that from DC that we have this constant gain, we get a minus 3 dB from that point. Okay, so why is that analysis important? It's just because if we know the frequency at DC, that this is the gain that we have, and we want to reduce that by 3 dB, we basically need to figure out what's the frequency that makes this term here 3 dB. Okay, and remember, this is in linear scale, so for 3 dB we just have to use the linear correspondence of 3 dB, and 3 dB is just means that the power of our output becomes half of the power of our input. Okay, and that, if you remember, in the linear scale corresponds to an amplitude of 1 over square root of that. Okay, so if we take the amplitude as like power, it's proportional to voltage square. If the voltage, it reduces by 1 over square root of 2, then basically that means that our power, which is 1 over square root of 2 squared, is just 1 over 2, it's halved. Okay, so the 3 dB point. So remember that once we have our gain reduced by 1 over square root of 2, that should be equals to that 1 over square root of 1 squared plus omega c r2 squared, right? So if you look at this equation here, we must have this term here inside the square root equals to this term here inside the square root. So this gives us that 1 plus omega c r2 squared should be equals to 2, right? Now if you put this on the right hand side here, negative, it becomes that omega squared c squared r2 squared is equals to 1. So this means that omega squared is equals to 1 divided by c squared r2 squared, right? And this, if we take the square root on both sides here and there, this is equals to 1 over c r2. So exactly at this frequency here, we have our 3 dB frequency. Exactly at this frequency, we have the magnitude in dB as 20 log 10 of R2 over R1 minus 3 dB. Okay, exactly at this frequency, the magnitude of the gain is this number here. Okay, so that's why we have the 3 dB point here, because no matter what's the value of R2 and R1, of course it depends on the design that we have, exactly at this frequency, 1 over CR2, we get this gain here. That's 20 log 10 of R2 over R1 divided minus 3 dB. Okay. Yeah. So for part E, then we have to design an amplifier. So let's see what's the requirements. So first we have to design the components to provide an input impedance of 5K. So let me go to the side here. So first we need an input resistance of 5K ohm. We need a DC gain of 50 dB. and a 3 dB frequency of, so omega 3 dB equals to 1 kilohertz. Okay, so using all the equations that we derived on part C, D, and on part B, we can actually define, and not especially part B, but using the knowledge of the input impedance of, or the input resistance of this circuit, we can basically define the values that we need for R1, R2, and C. So first, the input resistance. Remember that this voltage here is 0, right? If this voltage is 0, we have, so let me erase this current here, because now I'm going to assign a current in a different direction. So if we have a current flowing in this direction from our input voltage V1 here, we know that the input impedance, the input resistance, is equals to that VI divided by that current that I'll call I1. Right? But you agree with me that if this is 0 volts and this is VI, right? Using Ohm's law, this I1 is exactly VI minus V minus divided by R1. And this one here is actually 0. So this means that our I1 is exactly VI divided by R1. So if we substitute this in this equation here, we figure out that our input resistance is equals to R1. Or for a design point of view, our R1 should be equals to our input resistance. So this gives us, from the design specification here, that R1 should be 5 kilo ohms. Okay, now we want a DC gain of 50 dB. So in linear scale, that corresponds to 10, 50 divided by 20, which is approximately, let me see, 316.22 volts per volt, right? So this is in linear scale. Now remember from the equation that we derived for the DC gain, that the DC gain, so 316.22, should be equals to R2 over R1, right? We know R1, we don't know R2, so R2 in this case is 316.22 times R1, which is 5k ohms. Okay, this gives us an R2 that is equals to 1.58 mega ohms. So that's the second component, right? But we still have to define the capacitance. How do we define the capacitance? It's basically from the 3 dB frequency specification, right? So we want that the 3 dB frequency is exactly 1 kilohertz, right? So this one here I wrote like 1 kilohertz, but that's actually not omega, it's the frequency, right? So for omega we need to multiply by 2 pi. Okay, so if we isolate C in that equation, right, C is equals to 1 over 2 pi times the 3 dB frequency times R2. Okay, and this means that it's 1 divided by 2 pi times 1 10 to the 3 times R2, which is 1.58 times 10 to the 6. And this gives us a capacitance of 0.159 nanofarad. So we have our C here, we have our 2 here, and then we have R1 right here. Okay, so those are the 3 components that we have to define based on this design specification. Okay. So I call it part F. So what would be the unit gain frequency for this circuit? So the unity gain frequency of this circuit, we just have to take the equation for this. It's kind of the same that we have. So we have the magnitude here, right? This is for the magnitude. We just have to verify at which condition or at which frequency, based on R2, R1, and C, the magnitude here is equals to 1, right? So let me call it part F. So we have the unity gain, the magnitude, should be equals to R2 divided by R1 times square root of 1 plus omega c R2 squared, right? So if we square both sides, leads to 1 equals to R2 squared divided by R1 squared times, now we get rid of the square root, 1 plus omega R2c squared, right? And if we basically multiply the rest is denominator multiplying 1 on the left side, we get R1 squared plus omega squared R2 squared R1 squared c squared equals to R2 squared, right? Now if we isolate omega in this case, omega squared is equals to R2 squared minus R1 squared divided by c squared R1 squared R2 squared. And if we take the square root of this means that omega is equals to square root of R2 squared minus R1 squared divided by c R1 R2. So that's the equation, okay, for the unity gain, for the frequency at unity gain. So if we substitute the values that we have for R2, that is 1.50, let me see, 1.58 mega ohm, R1 equals to 5k ohm, and capacitance 0.159 nanofarad, we get a frequency omega that is equals to 1.25 megaradians per second, right? Or a frequency that it's equals to 200 or approximately 200 kilohertz. Okay, so we are done with the unity gain. Okay, then the last part is just like plot the Bode plot. Okay, so I'll put part G here. So remember that for the magnitude of h of j omega, we have R2 divided by R1 square root of 1 plus omega R2c squared. And for the phase, right, for the phase here, we have 180 degrees from the minus sign that we have on the voltage transfer function, right, minus the arctangent of omega c R2. Okay, so how do we get the phase, right? I know that sometimes we have some struggle figuring out how to calculate the phase. So let me first write the linear transfer function here. So the linear transfer function h of j omega is equals to minus R2 over R1, that multiplies 1 over 1 plus j omega c R2. So that's the linear voltage transfer function, right? So the magnitude we got by basically taking the magnitude of each one of the components, right? And then we multiply the magnitudes, like writing in the polar form, okay? But if we write this in the polar form, so we get R2, and the angle of this R2, because we have a minus, it's 180 degrees, right? And then we divide that by the magnitude of R1, which is just R1, with the angle of 0 degrees, right? Because it's just a real number, R1. But then this complex number here, we write its magnitude as square root of 1 squared plus omega c R2 squared, right? The square root of the real part squared plus the imaginary part squared. That's the magnitude of this complex number. And the angle we calculate by the arctangent of the ratio of the imaginary part divided by the real part. So this is the arctangent of the imaginary part, omega c r2, divided by the real part, divided by 1, right? So if you look at this equation here, r2 divided by r1 times square root of 1 squared plus omega c squared, this is the magnitude that we have here, still in linear scale, right? Now if you look at the phase, remember that if you have complex numbers in polar form that are multiplying, we add their phases, right? So if you think of the phase, we have here at the denominator 0, so let me write 0 degrees from R1 plus arctangent of omega CR2 divided by 1 is just omega CR2, right? And why I put this in parentheses? Because remember that this 0 plus arctangent is the overall phase of the denominator, right? So if we have like 180, like a polar number here in the numerator divided by something in the denominator, we subtract the phase of the numerator by the phase of the denominator. So it's 180 minus this phase, which results in 180 minus 0 is just, we just ignore that, minus arctangent of omega c r2, which is the same equation that I wrote up here. Okay, so if we plot this one here for several values of omega and we take like 20 times log 10 of that value, we get the magnitude of the Bode plot. If we change w or omega here in this equation, we basically get the phase for the Bode plot, okay? And the Bode plot for this case, so if we plot the magnitude first, that goes right here. So let me just zoom in a little bit. It's easier for me to draw. So we have here the magnitude. So this is the magnitude. And for the Bode plot, we use the dB. So remember to take the magnitude, the linear, and then take the log 10 of that and multiply by 20, okay? So we have 20 here, 40 here, and 50 there. So 50, 40, 20, 0, and I'll put here minus 20, okay? So if you select like several values of omega, and I will specify some values here, so 10 to the 1, this is omega in radians per second, 10 to the 2, let me see, I have to go up to 10 to the 7, so 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, it's here, 10 to the 7. So if we get what's the 3 dB frequency, right? So the 3 dB frequency, it happens exactly, we have calculated, it happens exactly at, we want that to be at, let me see, it's 100, it's 1k ohm. So at 1k ohm, we have, so at DC we have 50, right? So at DC we have 50, but exactly at 1 kilo, so it should be 1 kilo, but that's not exactly 10 to the 3 radians, right? That would be the same as 2 pi times 1k, which is roughly 6 something. So it would be, let me calculate it pretty quick. So this is 6.28 10 to the 3. So it's right around here. right? So this point here, it's the 3 dB frequency around this region here, and that is exactly 50 minus 3 dB, so it's 47, so it's around this region here, right? Now if we are like 10 dB lower than that, we are most at around here, and 2 decades below that it's around here. This is just like low frequencies, so we are much likely to be here around 50. Okay, you can calculate the exact value. It's going to be like around 50. Even here it's going to be around 50 because that's the DC gain that we have specified. Okay, now we also have calculated the unity gain, right? The unity gain frequency, and the unity gain frequency we calculated it's around 1.25 mega radians per second. So 1 mega it's exactly here. Now 25 it's around almost here. So this is another point of interest that we have, right? And this basically gives us the plot of the, so if we connect the points here, so here we stay at DC, then we start to decrease here, and then here we just go right away down to unity gain here, and this basically decreases by 20 dB per decade. Okay, for the phase, we just have to calculate some values here again, so 10 to the 1, 10 to the 2, 10 to the 3, 4, 5, 6, 7. One. So exactly at the 3 dB frequency here, we go from 180 all the way down to 135 degrees, and then here is 90. So exactly it's so 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6. So exactly around here, where is the 3 dB frequency, we are exactly 45 degrees below 180, right? Because if you look at the phase here, if omega here in this case is equals to 1 over CR2, which is our 3 dB frequency, right? Then this term here becomes arctangent of 1, and arctangent of 1 is 45 degrees. So if we take 180 minus 45 degrees, this gives us exactly 135 degrees here. Now for lower values of frequency, so for 10 to the 3, I got something that it's around 174 here. Then this one is closer to 180, 10 to the 1 it's even closer. Down here 10 to the 4 is something around here, 122 degrees. 10 to the 5 it's something around 92, 94 degrees. Then 10 to the 6 we are closer and closer to 90. So this is the phase. Okay, this is the phase that we get. And if we keep increasing the frequency, eventually we will end up like to just to 90 degrees. So we stay constant at 90 degrees. Okay, so that's the Bode plot. You can check on these solutions as you learn. You see that we have like better plots. Forgive me about my handwriting here, but that's basically the asymptote behavior of this particular case. Okay.